I'm 𝗕𝗃𝗀𝗃𝗀𝗀. I'm an application scientist at SCIEX. Prior to working here at SCIEX, I worked in our biopharma industry for quite some time. In that time, I was mainly working in analytical development for different bioproducts. I worked on mAbs, I worked on bispecific antibodies, I worked on fusion proteins, insulin products, nucleic acid, even an ADC project. But at SCIEX, I've really been exposed to a lot of next generation molecules in the last number of years. And I've really had to leverage that background in protein separations to develop methods and to adapt methods for these next generation biologics, such as AAVs, which we're here to talk about today. So we'll be discussing a CE-SDS workflow for AAV capsid protein analysis that can be used, and I've used, to help determine not just AAV protein purity, but also AAV capsid ratio. And we can use it to determine AAV capsid titer. So let's start by just taking a few minutes to really review the background and the analytical characteristics of AAVs. And we'll also overview the CE-SDS method in general for AAV protein characterization. So adeno-associated virus, more commonly known as AAV, as I've been talking about it, is really one of the most common gene delivery vehicles in our industry in gene therapy. Really is due to its non-pathogenicity and its low immunogenicity in our patients. It also has a fairly broad tropism, right? So it's able to infect multiple cell types, be used towards multiple indications. Now, AAVs are relatively small viruses in the world of viruses, but in truth, compared to our proteins, they're enormous. They're in the megadalton range. Now, the shell of this AAV capsid protein really contains three major components. We have our VP1, our VP2, and our VP3 proteins. And they exist in a theoretical ratio of about 1 to 1 to 10. Although, experimentally, it's rarely seen. And the AAV genome, the encapsulated genome, is a single-stranded DNA genome. That's about up to 4,800 bases in size. So we have this very large capsid that's made of 60 different protein subunits. And an intact capsid is, like I said, very huge, in the megadalton range. So we have to understand how to break that capsid down to get an idea of really its quality, right? We need to see that capsid purity assessment, both for our quality assurance, for our patient safety, because it's a regulatory expectation. And we need a very high sensitivity detection method, mainly because the titers of viral vector products are very low, whether they're coming out of cell culture, different process development stages. The titer is just low, especially by comparison to more traditional protein therapeutics. And to reach those high sensitivity, we're really going to leverage CE-SDS with laser-induced fluorescence detection. So we're going to get a look at the individual capsid purity and also see the increased sensitivity that only a fluorescent dye can give us. So if we look at some of the other technologies that are out there, they do have challenges. SDS Page has been around for many years, long before I ever started in industry. Right? But it's not a fun assay to run. It's very manual, very messy, destaining, putting on densitometer, integrating that way. Your results are at best semi-quantitative. Your precision is never great. Your resolution can easily be improved. So we might try a more 21st century technique, right? Like reverse state HPLC. And it's okay. But we don't want to settle for okay. And the problem with the reverse phase is, well, our resolution isn't always great, as we can see there on the right-hand side. But the other problem is the resolution of the peaks is really serotype specific. So the elution order of the peaks that we get can be all jumbled up. Sometimes we'll get better resolution, sometimes we won't. And we don't know which peak is which when we first see the molecule coming out. So right off the bat, we have to do some intensive characterization to say which peak is really which. You can take a have a pretty good idea that VP3 is our most abundant peak, but the other two could easily be co-eluting. And where we also miss potentially our VP3 prime peak that we commonly see with CE-SDS. Not only do we lack the resolution, but we lack sensitivity. And with SCS Page, we definitely lack quantitative analysis and a lot of precision. Now, CE-SDS does give us a very nice size-based separation, as we see here. So we're going to take our protein, and it's going to be really just coated with SDS molecules to give it a uniform negative charge that's relative to its size. So our separation is really based on the hydrodynamic size then of our protein. And what we'll see is our smallest, most mobile proteins migrating first, coming past our detector first. So we see our VP3 prime peak, followed by our VP3, then VP2, VP1. We can get really unmatched resolution here, and we always know which peak is which because we always have that size-based separation. It's not being driven by an interaction between our protein and the stationary phase. So now I'd like to take a moment to show you really an overview of the Biophase 8800 system that we'll be talking about today. And that really does enable this high throughput, high resolution CE-SDS workflow where we can look at purity, VP ratio, and also estimate our titer. All right, so the Biophase is right over here to my left. One of the first things you're going to notice with the system when you walk up to it is the touch panel, the front panel. Front panel is a touch screen, sort of tablet design here. Got a number of different buttons here that we have tiles that we can press. We directly control the instrument, run our sequence from this front panel, take a look at the capillary view, what's actually being run. And if we just slide it over, we reveal a nice hidden compartment. Right in here, this is actually where our capillary cartridge gets loaded in. And right here is where our coolant gets added to our system. So this Biophase 8800 system has the same recirculating liquid coolant that you're probably used to on our single capillary P800 Plus to maintain that really robust migration time that we really know and love on this system. And then right just beyond that is our sample and reagent tray where those are going to get loaded. And if we look back on our front panel on this top right, we can see that we have both the LIF and UV buttons there. So what's sort of unique with the Biophase 8800 system compared to some other systems is we have both detectors on board at all times, which means that there's no more user interaction to take any detectors out, put new ones in, turn it off, recalibrate anything. They're always there, ready to go. And we can leverage this even further. We can use both detectors within a single sequence that we set up. So we can start our sequence, say, our first 5 samples with LIF detection, and we go to the next 5 samples with UV detection with no user involvement. Now, our method that we'll be discussing today, the CE-SDS analysis with laser-induced fluorescence detection, does use a more unique filter, a 600 nanometer filter, for our fluorescent dye. Now, it's actually very easy to replace. We can go on that direct control. We can go down to wavelength settings. We can click over there to the LIF wavelength. There's just a button here to replace the filter. It'll show you here that right on the side of the instrument has a door that's going to pop open. And all that we're going to have to do, here's a look at the actual filter that we can replace. It slides right in just like you would a USB drive on your computer, and you can just slide the other one right out. And once you're done, you click done, go back here, update the emission wavelength, and you're ready to go. So you can move from nucleic acid analysis that might use a 520 nanometer filter to protein analysis, which will use more often than not a 600 nanometer filter very, very quickly, very easy to do. All right, so let's take a look at some of these. So, like I mentioned, the Biophase is a multi-capillary system. It actually has 8 capillaries that it runs at a time. So this is a look at our Biophase cartridge. It's all pre-assembled, no user involvement here. And on the inlet side of the capillary, you can see all 8 of our capillaries. Each one has its own electrode that surrounds the capillary and just a small exposed capillary tip. And then the 8 will come up this way and go over to the detection window. You see there? And then they all come out bundled together on the outlet side right there. Now on the outlet side, they all share the same common electrode right there. Now, one thing I will mention is that we don't have apertures that you need to change either. There's really no user involvement. At the most you're going to do is just look at the bottom here, wipe down this O-ring with a wet Kim wipe, and that's really all that I've ever had to do when preparing this cartridge. Now, if we flip it over, we're going to see the coolant ports where the coolant is going to be going in and out of the capillary, recirculating through the capillary. And then the smaller O-rings on the side, that's where pressure is being applied. So pressure is no longer being applied toward the bottom of the capillary where our reagents are. Pressure is being applied here on the back, so there's really no way for any reagents to get into our pressure lines like there are with some other systems. Now, you might also notice over here we have an RFID chip. That RFID chip is going to have all of our capillary information, the serial number, lot number. It also tracks the data first use and the amount of runs that have been put across the capillary. Now, we do not limit you on the amount of runs that you can use it for. So, you run it for 100 runs, use it for 400 runs. You just keep on using it while it's giving you good data. A multi-capillary system is going to use different trays. So here we have our reagent tray in front, and this is 96-well plate base. It is ANSI, so you can use it for all automation if you like to use a Hamilton, you like to use a biomech system. Those are all compatible with our hardware here. And each capillary is going to go into its own independent reagent well. So each one is going to be rinsed independently. Each one is going to be electrophoresed independently. And then on the outlet side, we use more of a trough-based system. So here, all those 8 capillaries will go into the same location as either a waste vial or the other end of our electrophoretic separation. Sample tray is also 96-well plate base. So we can see each individual well here for our samples. And it'll also have its own outlet reagent plate. And we can see with each of those, they have sort of this tapered corner to ensure that it is loaded into the instrument correctly. And for the sample and reagent plates, you can see it has a little key here. So the sample plate has a key on this side. The reagent plate that I just had on the screen has a key on the other side. This is just to make sure you don't accidentally put them in the right spot. So you can't really put this sample plate where the reagent plate should go. Now, let's take a look at our kit. So here is our Biophase CE-SDS protein analysis kit. And if we open it up, we're going to notice that we have a lot of color going on, which is something new and unique to Biophase. And I really think it's a great feature that they added in. So we have individual storage boxes within the kit. And they're color coded. So this one over here is green. And the green signifies it should be stored at refrigerated conditions. So it's already in a secondary container. You can just take it right out of there and put it in your fridge. The orange one over here, this is to be stored at ambient conditions. So again, in its secondary container, very user-friendly. You also notice that we have different colored caps. So each reagent has its own colored cap. Our basic wash has a blue cap. Our acid wash has a red cap. Our gel buffer has a green cap. And that's definitely by design. So here we're going to, in our Biophase software, which we'll touch on in a few minutes when we get over there, all these colored caps are going to match the color in the software when we're loading our reagents. This just gives the end user a very nice visual indication of which one is going to go where. Because when you are loading up reagents in 96-well plate, there are quite a few, there's quite a bit going on. So it does definitely help keep everything straightforward for you. All right, that's pretty much a good look at our reagents. So before we continue on, let's just do a quick overview of the sample prep that we use to really analyze these samples. So for our CE-SDS analysis with standard UV detection for AAV purity and VP ratio, we typically start with just doing at least a 1-to-1 dilution of sample into our sample buffer. And that really depends on the titer, the concentration of our initial starting sample. We'll have that 1-to-1 dilution, then we'll add a certain amount of reducing agent. Typically for UV analysis, we'll add 𝗕𝗵𝗀𝗃𝗏𝗏𝑒𝑡hanol. And then we'll heat it for a certain time at a certain temperature, and that is really serotype dependent. Certain serotypes are going to need a little bit more heat to fully denature the proteins. Other ones will more readily sort of denature and break apart the capsid. Now, for our lift detection, we can have a very similar workflow. So we can start with just that same dilution in the sample buffer and the addition of a reducing agent. In this case, we typically use DTT. It doesn't have quite the smell of 𝗕𝗵𝗀𝗃𝗏𝗃𝗏𝗃. And then we're also going to heat it for a certain time and temperature just to fully reduce those capsids and denature the proteins. Then we can add our fluorescent dye and heat it again to get that dye conjugation step going. And once it's conjugated, then we're set to go. Now, some of our customers have developed more unique workflows that worked well for them. Some of them have just gone to a single dilution. So they add their sample buffer, their reducing agent, and their sample along with the dye at the very beginning prior to heating. And then they'll heat all of those together. So there's definitely room for optimization for each product, both around the heating time, heating temperature, and the ratio of all the different components. The Biophase software is completely built from the ground up. It was built really with the end user in mind. So with Biophase software, we have, again, these tiles here, and we start with this tile called our reagent editor. And our reagent editor, the idea behind that is we no longer have static locations where our reagents are going to go. So our water is not necessarily in position A1 anymore. Our gel buffer isn't in B1 and C1 anymore. We've really made it more dynamic, or you can put it wherever you want it to go. The other really nice thing is the software can calculate the volumes used, the actual volumes used of each reagent based on its viscosity, the amount of applied pressure, and the pressure duration. So here, when we look at our CE-SDS reagent, which I already have open, what we have listed is all the reagents that'll ever be used on our inlet side of our capillary. So we're still using the same acid and basic wash, still have the same gel buffer rinse and gel buffer for separation, the same water rinse and different water dip steps. So they're all the same that we would see on our single capillary p-Adern plus instrument. But what changes is just that there's no longer a location for those to go. Instead, we just define that they're there somewhere. Next, we see that we have viscosities listed for each individual reagent. And again, that's so that the instrument can calculate how much volume is going to be used. And then it'll tell you when you need to add more to a new reagent column, reagent well column. And then finally, you see the colors over here. Now, as I mentioned when I was going over this, the kit with the different colored caps, each cap then is responding to or corresponds to the color listed here. So our basic wash is that blue cap, our acid wash is that red cap, and our gel buffer are the green cap. And then our water just sort of had that opaque, somewhat clear, transparent cap. Now we also have to define the buffers used in our outlet tray. So in our outlet tray, just like our outlet tray on our single capillary instrument, we have our waste, we have the gel buffer used for the separation, we have water used for water dip, and we have the gel buffer that's used for sample injection. So everything is just defined, but there's no longer a static location. Now, once we have defined these reagents, we then have to go and build a method. So you can go ahead and open up your method if you already have one. You have just one over here, our lightning method or just our standard CE-SDS methods. The first thing that you're going to want to do is choose your reagent file, because everything is going to be built off of that. So you choose your reagent product, then you can choose your reagent set, and then you can start filling in all of the information that is probably fairly similar to what you're used to. So you have your cartridge temperature, your sample storage temperature. You can add in your capillary length and the type of capillary, whether you're using UV or lift detection, the data collection rate. And then over here, we see our reagents listed. Now, the final thing that we do, we just go from tab to tab to tab. Everything is very linear here, is our method program. The method program is just drag and drop. So you have all your actions here at the top, and all you have to do is drag them down. And then you can choose from these drop-down menus what you want to do. So here we go on basic wash into waste. Now you say, oh, I already had my basic wash. Go ahead and throw that into the trash. So here are all your actions in blue. Then you have weight steps for your water dips in orange. And what's unique for our AAV purity methods is we really utilize what we call field amplified sample stacking. So here we're introducing a water plug prior to our sample injection, really to create a difference in ionic strength between that water plug and our gel buffer. And what that helps to do is it gets a lot more sample introduced with our electrokinetic injection. And the sample is going to stack at that interface between the water plug and the gel buffer. And thus you get that field amplified sample stacking acronym, FASS. Now, after our sample injection, we'll do another water dip just to clean off the end of the capillary, and then our separation. And after our separation, we'll go to another water dip step. So this is going to look very, very similar to our P800+ method, but again, I haven't defined any locations of our reagents. All that I've done is told the instrument to go from one reagent into another reagent, whether that's from a wash buffer into a waste buffer, or from a gel buffer into another gel buffer for a separation. Something like that. So we have defined our reagent set. We have defined our method, in this case for CE-SDS with lift detection. We did go over that field amplified sample stacking that really gives us unparalleled sensitivity. So now we just go to our third tile, the sequence editor. What I probably want to do then is go to new. Let's just go ahead and build a completely new one. So we'll start here. And we'll click on the folder that has our methods. And down here in the bottom left, you can see our 96-well plate. The first thing we want to do is to just condition our capillary. So when I drag this down, we can kind of see it highlights the whole plate. We have a nice yellow border because it's not injecting out of any well. But once we drop that off, then it will start to populate over here. Now, let's say we have six columns of samples. We can take our AAV purity with CE-SDS lift detection, and maybe we're going to run that in our first 3. So in our first column, for example, we can generate a standard curve to do that titer estimation I've been alluding to. In our second and third columns, maybe that's our unknown samples. And then for our fourth, fifth, and sixth column, maybe we just want to do a standard UV analysis. We have some other therapeutic we're trying to analyze, or we have a higher concentration AAV product, or we just want to do a comparison. What does our lift look like compared to our UV? All that it takes is just dragging down a different method onto your 96-well plate here. And then everything gets populated over here to the right. Now our shutdown method, we can drag this down. Again, it's going to highlight the whole plate. One thing I did not mention so far is that all of our conditioning and shutdown methods are the teal color. Those are separation methods are the dark blue. And the instrument knows that they're different because when you have a sample injection, that will designate it's a separation method. And it'll give it that dark blue color. If there's no sample injection, then it'll give it that teal color. The last thing we might want to do is add this error recovery method for our shutdown. So if the instrument does run into any errors, it's not just going to sit there until you come back to it, over the weekend or after holiday break, right? It'll go then to your error recovery method, run that method, which will shut the system down. You're not wasting your lamp hours, your lift hours. It'll make sure that the capillary is stored in a safe environment. So we've got our method, our sequence. We've got our sequence laid out how we want. Now we can go to the plate layout. And this is really where we see a nice feature of Biophase. And this is that dynamic feature of where your reagents go. So it's sort of defaulted like this. As we added methods to these different columns, the software starts populating where the reagents are going to go based on the order that they're going to be used. But when I do it, I like to move all of my reagents into a certain order so that I can pipette them all together. I find this to be incredibly intuitive. So here I've just moved all of my water columns over to the left to get those all together. Then I have my basic wash sort of in the middle, my acid wash following that, and then my gel buffers are at the end. We can also see up here, this is that trough setup for that outlet reagent plate. You can see in the black is our waste, in the blue is our water dip, in the green is our gel buffer. That's also designated down here by sort of the legend. So here we are back at the front panel. So we need to do a few things. The first things we're going to do is to go in this direct control. We're going to load our sample tray. So we'll go ahead, eject that sample tray. Put the tray in there. And then once it's done, just go ahead and load it. We'll have to do the same thing for the reagent tray once the sample tray is finished loading. And then we'll add our cartridge in there. And we can come over here, take our capillary cartridge, and this is just going to slide right in. How simple that is. Slides in. You feel it kind of lock at the end. And then a button right there at the top of the front panel is going to lock it into place. Now that we've got everything in there, we can go to our run sequence over here. Select our AAV Masterclass. And it loads up right like this. And this is a great opportunity to do a double check of, what? Did I write the right method? I just click there. You can scroll down and see the method that you have ran. You can hit there in your sample, get a nice zoomed in view of your sample tray. You can touch over there on your reagent tray, and you can see exactly where your reagents are, just to make sure that you have put everything in the correct spot. Let's take a moment here and look at some of the other things that we can do on this front panel on this direct control screen. So under direct control, we have a lot of the same things that we can do on the P800+ instrument. We can manually set our cartridge or sample temperature. We can do manual rinses if we want to. We can choose our reagent tray or our sample plate. We can do manual injections from either our sample or reagent plate as well. You can do manual separations, right? All the things that we might use from time to time to troubleshoot, you can do exactly right here. We already saw that we can change our wavelength settings there. Right here, we can look at the cartridge info with the cartridge that's been installed. And then down here at the bottom, when our separation is occurring, we can see exactly what's going. So we'll see the system status, how long it has on any of the actions, any of those separation, what method is being run, what all of our temperatures are, our applied pressures, applied voltages, generated currents, coolant level, user, etc. With that, we have the run sequence that we looked at really quick, which is very nice. You can just sort of scroll up and down. The last thing that we haven't taken a look at is the capillary view. So this is kind of nice. You can actually view all 8 capillaries independently like this in a tiled view. You can overlay them like this, where you see all 8 separations occurring at the same time. you can also look at the current, the generated current. Or if you want to, you can go to a mixed view. So you can look at the optical trace as well as the current trace at the same time. Now, if you're not running all 8 capillaries, all you have to do is uncheck the capillaries you don't want to look at. So, as I kind of mentioned earlier, one of the things we want to do when we're inserting a cartridge is just to make sure that we're wiping down those O-rings. That's really the only user involvement. From run to run, when we're done, when we're putting in there, you just wipe down the O-rings on the cartridge. And that's about the only thing that we need to do. We're no longer rinsing down the interface block. The interface block really isn't interfacing to the bottom of the capillary, so there isn't any chance for that residual chemistry to get caught on there, which is very nice. But now that we've gone over everything, we can go ahead and run our sequence here. There we go. So here we are back on the Biophase software screen. And we've gone over the reagent editor tile, the method editor tile, and the sequence editor tile. So now we're going to go ahead to our data analysis. So the first thing we're going to do is just open our data files. I'm going to take a look at these first two. We have an AAV2 serotype here that was collected with the UV detector. And then we have an AAV8 serotype here that was collected with our lift detection. Now over here on the right-hand side, you'll see a lot of our integration parameters. And this is just like our processing method parameters that we're used to with any other chromatography data software. So you can set those to, we have a lot of different options here to set and optimize our parameters. And once you have them set, you can go ahead and save that processing method. And that's exactly what we're going to do. We're going to look at an old processing method that I already have. We're going to open that up. And then we click here on the little play button, and it'll analyze our sample. So here we've got, a couple of small peaks here on the front end. And then we've got back here our VP1, VP2, VP3, and our VP3 prime, which for a number of products we found is just a truncated form of VP3, which is slightly smaller in size. Now, if we look at this, we're right about, so right about 94% purity if we're adding up VP1, VP2, and VP3. So 94% purity, that's pretty good. And the sample exists in a VP ratio of about 7 to 1.3 almost to 1. So you have a good idea of your purity. You've got incredible resolution. You know exactly which peaks are which. You see some of the smaller related substances potentially. You get an idea of your VP ratio. Now, that's a pretty good Titer sample. And we can use our UV detection on. But what about, like you mentioned, those in-process samples? Well, that's definitely where lift comes into play. So we're still using the same separation buffer, still getting the same resolution between the peaks, but we have much higher sensitivity. So we'll go ahead and open our lift analysis method now. Go ahead and analyze that. What we can see kind of right off the bat is that there's quite a few more peaks that have been found. Right? We have about 5 different peaks here in the front end. And zoom in over here. And yeah, they're real. They're there. They're definitely not baseline. The lift gives us an incredibly clean baseline, which is really nice. And the software is also very to use. So if we want to split a peak like this, we just hold down Control, left click, and then we can right click here and split the peak. And if you might say, you know what, I don't really think this is a real peak, we just right click and delete the peak. It's very easy to use. We can zoom out here. Here we see our VP1, our VP2, our VP3, and our VP3 prime peaks. And this one has a purity of, I would say, about 93%, roughly adding, well, I was adding up the area, not the corrected area, but still probably about the same, about 93%. So maybe about 7% related substances that aren't our primary VP1, 2, and 3 peaks. And then the VP ratio probably also exists in a ratio of about 7, just over 7 to 1 to 1. So that's something that I've definitely talked with customers who are monitoring this, monitoring their cell culture process, how that affects the VP expression, and how this VP ratio also can affect the efficacy of a product down the line. So how that capsid is coming together out of cell culture can obviously have a big impact, not just the purity of the capsid and how many related substances are there, but how well it actually came together with those subunits. And we've also, alluded to how we can set that sequence up to generate a standard curve at the beginning. We can also set our sequence up to really help optimize our method. So with 8 samples being injected at once, you have opportunity for 8 different sample prep conditions to be analyzed all at the same time too. So within under an hour, you can look at, say, 4 different heating times, 4 different heating temperatures. You can look at different concentrations of SDS. You can look at different sample prep workflows, whether you're doing one heat step or 2. You're adding that fluorescent dye separately, or whether you're adding it at the beginning in sort of a more reaction mixture. Now that we've really looked at that, right? We've really seen some good high sensitivity data here with the CE-SDS lift detection. We've seen some really nice data with the UV detection. Let's take a look at that titer determination and what that looks like. So here is taking a look at that titer determination, right? So we can, as I mentioned, that you take that one column of samples, you label your AAV with a known titer, and then you can just do a very simple serial dilution. And here, they've gone from about 2.6 or so e to the 13 GC/mL down to an incredibly low limit of detection, limit of quantitation, below 1 e to the 10 GC/mL. And when you generate this standard curve, we're really looking at the corrected peak area against the concentration. And here we see an R-squared of about 0.99 or above 0.99. So we have very good linearity of response compared to that peak area. And it allows us then to take our unknown peaks and apply it to this standard curve and get an estimate of what that titer is. And this can be much more robust than some more conventional, well, I wouldn't say more conventional, more widely used techniques like ddPCR. So there we're really using, looking at the encapsulated genome. Here we're taking a direct look at the protein titer. We're not looking at genomic titer. And when we calculate this capsid protein titer, and we'll actually do this in our next webinar, if you're here for the next webinar, we're looking at how we can leverage this capsid protein titer determination along with a genomic titer determination that we're going to get from our genomic integrity assay, how we can put those two together to get an idea of what the true empty full ratio is of our sample.